Hello friends, welcome to GT Science tutorial. In this video, I'm going to explain about crystal growth, or more precisely single crystal growth. This is a very important concept in solid state chemistry, as a growth of single crystal is required in many types of studies. So in this video, we will understand what single crystal growth is, and we will see different methods to grow a single crystal. So let's start. First of all, we need to understand what crystal growth is. So suppose we have different nuclei like this. We have different nuclei like this. Now, due to some reason or due to some procedure, let us consider those nuclei come closer and closer and make an aggregate in a regular manner. Then we call that crystal. We call that crystal formation, right? So it is the process where a pre-existing crystal, these are crystal sheets, okay, becomes larger as more molecules or ions added in their positions in the crystal lattice, or a crystal is developed from the solution or vapor, and further growth is proceeded. So a pre-existing crystal will be there. According to the definition, a pre-existing crystal will be there, and different other molecules or ions from vapor or solution comes there, and they take their respective crystal lattice point. Then the size of it will keep on growing, and a crystal will be formed. A crystal will be formed, and that is processed further. That's called crystal growth. Now let's move forward. Now we need to understand about characteristics of a single crystal growth. So what are the characteristics of a single crystal growth? I'm going to explain 7 or 8 characteristics over here. Let's understand what are them. So the first one is, okay, it is an irreversible process. That means the crystals once formed cannot be reversed back to its original constituents. Atoms, molecules, or ions in a crystal lattice are trapped, hence they are fixed and cannot move from their position. So, when some atoms or ions come near to the pre-existing crystal, then they are trapped and cannot move at all. Okay, the atoms, molecules, or ions arranged into the correct lattice position, that is Brevis lattice. So they will be arranged in a correct lattice position in some geometrical form. A particle is joining the lattice at the point where its energy will be minimum. So let me explain this point with a diagram. You can see over here, I have put a picture over here. These are all the atoms or ions arranged at their crystal lattice. Now this red one, you can see this red one, the red atom or ion that is in cubic form now wants to go from here to, it can take any of the position, right? Suppose it could come over on top of this crystal, this atom or this atom. It could come over here, it could come over here, but it decided to come here at this position. So what may be the reason for that? Look at here. So, wait a minute. A particle is joining the lattice at the point where its energy will be minimum, right? Suppose if this atom or particle came over here, then what would happen? One face of this atom and one face of this atom, that is the bottom face, would join, and all the other faces will be exposed, right? Will not have any interaction with anything. The same thing will happen over here. That means only one face will be connected, joined. Now if it comes over here, then two faces, one face and two faces will be joined. Similarly, if it comes over here as well, one face and two faces will be joined. But if it comes over here, then one, two, and this, including these three faces, will be joined. So if three of the faces are interacting with other atom, then it will be stable, its energy will be minimum. You can see over here, I have written it properly in a simple way. The corner of the incomplete top layer, that is the corner of the incomplete top layer, has a minimum energy, because in that position, incomplete top layer, sorry, this one, okay, this one, because in that position it will interact with three neighbors. It will interact with three neighbors, 1, 2, and 3. All other positions on crystal layer have only one or two neighbors. So all other position, this or this or this or this, has only one or two neighbors. So it will definitely try to choose that neighbor or that position where its energy will be minimum, and that being where and that being this position, because 1, 2 and 3, these three positions or these three faces will interact with three faces of this atom or particle, that will minimize its energy. So I hope you understood this much characteristics. Now let's move forward. So other characteristics are, so the crystal growth technique determines the material's characteristics and also the concentration of impurity and defects. So crystal growth technique can determine the material's characteristics and concentration of impurities. If you already don't know about impurity, you can visit my channel. I've already put a video over there about the impurities in a crystal. Yeah. Now, uh, the techniques the techniques are typically based on reducing the solubility of the sample. So forming crystal means reducing the solubility of the sample. The sample solubility will keep on declining as the crystal is forming. Okay. Now, mostly solubility of the compound decreases with decreasing temperature. So if the temperature decreases, then solubility also decreases. We know that from the concept of saturation and supersaturation. If we consider water in a beaker, and if we put sodium chloride, then what will happen? It will get dissolved. If more of sodium chloride is added, then a point will reach when the sodium chloride will stop to get dissolved. That is called saturation condition, right? Now if we increase the temperature of it, then what will happen? More sodium chloride will be dissolved. That is called supersaturation condition, right? So we can simply say that in reverse, if temperature is decreasing, then the saturation also, or then the solubility will also decline. Okay, then the solubility will also decline. Hence, cooling of a saturated solution, once a saturated solution is formed and if we cool it, then that often produce crystals. So I've already spoiled it. So cooling of a saturated solution will often produce crystal. That is the process to form crystal. Now, rate of change of temperature determines the size of the crystal. Okay, so rate of change of temperature. So how quickly or how slowly we are changing the temperature, that determines the size of the crystal. Slow cooling leads to a few nuclei and large crystals, but rapid cooling leads to precipitation of amorphous solid or microscopic crystals. So you can see over here, suppose there are many nuclei like this. Okay, now if we cool it slowly, this is a slow cooling, then what will happen? One crystal will be over here, another crystal will easily form over here, another crystal will come and another sorry nucleus will come and attach to it, and as a result of that, the size of this crystal will keep on increasing. But if if in another case, if the temperature is decreasing, if a temperature is decreasing in a rapid way, then will these nucleus get enough time to aggregate properly? No. Then a lot of microcrystals will be formed, that is amorphous amorphous solid will be formed. So I have put it over here. So hence, nucleation and growth determines the size and purity of single crystal. So nucleation and growth determines the size and purity of the single crystal. If nucleation rate is slow, but growth rate is fast, larger crystal will result. I'll explain it later in the video. Similarly, if nucleation rate is fast and growth rate is slow, small crystals or even polycrystalline sample will result. So this simply try to say that, see, nucleation simply means, suppose these atoms are over here, these are the nucleus. Now if they come together to form aggregate, that is called nucleation. But if its size keeps on increasing, then that is called growth. Okay, a single crystal growth. Now if nucleation rate is slow, that means if these atoms are aggregating in a slow way, then what will happen? then the large crystals will be formed. Same crystal will keep on increasing. But if the nucleation rate is fast, if nucleation is happening quickly, okay, more and more crystal is coming over here, okay, then what will happen? The crystal size will be slow, but there will be a lot of crystals. We will understand it later in the video. So, crystal growth typically occurs via formation of solid from another state of matter. So, another state of matter will form a solid. Okay, that's how crystal is grown. Now, based on the phase transformation process, there are different techniques. They are over here. So, growth from solution, that is the first one. That is also called crystallization. Second one is growth from melt, that is called freezing. Growth from vapor, that is called condensation. And growth from solid, that is called, no, that is not called anything, that is just called growth from solid. So now let's understand them one by one. First of all, we will understand about solid solution or crystallization. We will understand only this much in this video. Okay, so growth from solution, that is crystallization. So, what is growth from solution or crystallization? Let's see it point wise. So, this is the most common and oldest method based on the crystallization from a saturated solution. So, first of all, a saturated solution is made, then the crystallization process is initiated. Now, materials which have high solubility and whose solubility depend on temperature can be grown easily by solution method. So those materials which have high solubility can be grown from solution method and whose solubility depend on temperature. That means changing the temperature will change the solubility of it as well. Now, the advantage of this method is that the crystals can be grown at temperatures well below its melting point, even at room temperature. So let us consider there is a crystal whose melting point is 200 degrees Celsius. So by this method, that is the growth from solution method or crystallization method, the same crystal can be made well below 200 degrees Celsius, around like 150 or 170 degrees Celsius as well. Okay, that is below 200 degrees Celsius. Now the growth from solution generally occurs in two different stages. They are called nucleation and growth. Now we will understand about nucleation and growth one by one. So, first of all, let's understand about nucleation. So, a phenomenon whereby a nucleus or a tiny seed starts to form by a crystallization process is called nucleation. So, suppose we take water in a beaker and we put some solid and dissolve it over here. Okay, suppose we want to make the crystal of sodium chloride and dissolve it over here. Now we will make a saturated solution, that is adding more and more solute, that is sodium chloride, until the sodium chloride will stop to get dissolved. So there will be sodium chloride over here, right? That will, this water will be filled by sodium chloride. A saturated solution will be made over here. Now if the temperature starts to decrease slowly, if the temperature starts to decrease slowly, then a nucleus or a tiny seed starts to form. Okay, somewhere in the crystal, somewhere in the solution, a nucleus or tiny seed will start to form. Not only one, but there will be those multiple of those tiny seeds. There will be a lot of those tiny seeds. These are called the nucleus or tiny seed. Now nucleation processes, so nucleation possesses a large energy barrier. So to form nucleus, a large energy barrier has to be covered, okay, or has to be overcome. That means it takes a lot of energy or effort to make the nucleus or to create a nucleation process, okay, or to initiate a nucleation process. Now to overcome this energy barrier, a supersaturation is required. So to overcome this energy barrier, that is initiate the nucleation, that is to form the tiny seed, supersaturation is required. I have already told you what supersaturation is. That means more and more sodium chloride will be added unless it stops to get dissolved. That is the saturation condition. Now if the temperature if the temperature is increased, then what will happen? It will be able to dissolve more and more solute again. That means more sodium chloride will be dissolved over here. That is supersaturation condition. Okay. Now the supersaturation can be achieved either by changing the temperature, or changing the pressure, or changing the concentration, increasing more concentration or decreasing the pressure. So these are different conditions by which supersaturation can be achieved. Now nucleation can either be homogeneous or heterogeneous. So, in homogeneous nucleation, there is a lack of influence of foreign particles. There won't be any foreign or any extra particle. Hence, can be carried out from highly supersaturated solution. So, highly supersaturated solution which do not have any foreign particles are homogeneous. Can initiate homogeneous nucleation. Okay. Similarly, in heterogeneous nucleation, there is the influence of foreign particle. There will be some foreign particle as well. That is some extra particle or some impurity over there. Hence, takes place more quickly because that foreign particle will behave as scaffold. Okay. Now, since the foreign particles can act as scaffold for the crystal to grow on, which reduces the surface energy requirement. Okay, suppose suppose there is water over here. Now there is sodium chloride put over there. Now if we put some impurity or foreign element, now this will behave as scaffold. That means the nucleation process will not have to uh, generate a lot of energy, or we do not have to provide a lot of energy to begin the nucleation process. Few nucleus will come and join to this impurity, and this will behave as the scaffold. Okay, it occurs spontaneously at metastable condition, that is small supersaturation. Now metastable condition prevents formation of many nuclei. It won't allow many nuclei to form. Similarly, the second one is the growth. Okay, so the growth is the subsequent growth of the nuclei that succeed in achieving the critical cluster size. So more and more nucleus will come together and form a single crystal. Okay, form a single seed. Now that will, if that attains a critical cluster size, if it has certain cluster size, that is the critical form of it, it will now start to grow. That means its size will start to grow. It will get bigger and bigger. That means the crystal is getting larger and larger. Supersaturation is the driving force of crystallization. We have already talked about this. Now hence the rate of nucleation and growth is driven by the existing supersaturation in the solution. So supersaturation is the driving force of growth as well. So as the growth proceeds, as the size is increasing, the supersaturation decreases. Supersaturation will start to decrease. To maintain a reasonable growth rate, to maintain a reasonable growth rate, the supersaturation has to be maintained. Okay, which is achieved by, so supersaturation has to be maintained at all cost to maintain a reasonable growth rate of the crystal. Now the methods that can be achieved the methods that can be used to maintain a reasonable growth or supersaturation are lowering temperature, isothermal evaporation, and flux growth method. Now let's see them one by one. Lowering of temperature. So how does this method help us to maintain the supersaturation? Let's see that. So this method involves cooling a saturated solution of a substance to induce crystallization. Okay, as the temperature decreases, the solubility of the solute decreases, leading to supersaturation. This supersaturation drives the formation of crystals. Look at here. Suppose this is the beaker in which there is water. Now, if we put sodium chloride or table salt in it and make a supersaturated solution, and after that, if we slowly cool the solution, then what will happen? Crystal will start to form, and with slow cooling, the crystal size will start to grow. And if we keep decreasing the temperature, the remaining crystals, the remaining sodium chloride will always form a supersaturated solution. That means if we don't decrease the temperature rapidly, then the supersaturation will be kept maintaining. Okay, this is the case. The temperature should be decrease slowly. This supersaturation drives the formation of crystal. So only condition is temperature decreasing slowly, because temperature and solubility are interconnected, right? If temperature increases, solubility increases. If temperature decreases, solubility decreases, and as a result of that, slow cooling will help to maintain the supersaturation. Now, so what is the procedure of this method? That is lowering of temperature method. Let's see that. So the first method, the first the procedure involves different steps. The first step is preparation of saturated solution. So here, dissolve the solute in a suitable solvent at a temperature above its saturation point. Ensure the solution is clear and free from impurities. That is the condition. Now, the next step is controlled cooling. So it should be cooled controllably, okay, with controlled environment. Look at here. Slowly reduce the temperature of the solution, often using a temperature controlled water bath or oven. So the temperature should be reduced slowly. A slow cooling rate allows for the for the formation of larger and more perfect crystal. The third one is crystal nucleation and growth. This is These two methods are very important. Okay, nucleation and growth. So as the solution cools, nuclei form. So with decreasing the solution, nuclei forms. Okay, nuclei forms, acting as starting point for the crystal growth. The rate of cooling influences the number and size of nuclei. So we have already talked about that. Slow cooling will make less number of crystal but larger crystals. But rapid cooling will make more number of crystals but smaller crystals. Okay, slower cooling generally leads to fewer but larger crystals. Now, crystal selection and harvesting, that is the fourth step. So here, once the desired crystal size is achieved, the solution is carefully cooled to room temperature. Okay, the crystals are then filtered, washed and dried. So this is the procedure for lowering of temperature method to grow a crystal. Now, there are certain advantages and disadvantages. They are simplicity. This method is very simple. Versatility and control over crystal size and shape. Okay, these are different advantages. Now, disadvantages are slow growth rate, risk of impurities, and difficulty in controlling nucleation. You can just pause the video and read this. These are very simple points. You can easily understand it. Okay. Now, similarly, there are certain application of this method. They are growing single crystals for research. So this method is very useful for growing single crystals for research in physics, chemistry, material science, etc. Similarly, industrial production of crystals, that is when crystals should be produced in industry, this method is very useful method for that. Now, additional considerations can be taken as seed crystal. So introducing a small seed crystal can accelerate the growth and improve crystal quality, that is impurity adding. Now, solution purity. High purity solvents and solutes are essential for obtaining high quality crystal. Now, temperature control. Precise temperature control is crucial for optimal crystal growth. So these are some of the additional considerations that should be taken. So I hope you understood about this method. Now let's move to another method. Isothermal evaporation. That is the second method to maintain the supersaturation. So in this method, that is the isothermal evaporation method, is a simple yet effective technique for the growing of high quality single crystals. It's particularly suitable for materials that have a moderate solubility in a specific solvent. So in this method, what do we do? Isothermal means constant temperature, right? Constant temperature. So, by maintaining constant temperature, the solution should be evaporated. Evaporation means reducing the amount of solvent, right? Suppose we take a beaker with solution, sodium chloride, sodium chloride solution. Now if we put a lid over it, with very small holes, that allows very small amount of particles or vapors to escape. Okay, that allows only a small amount of vapor to escape, and we can control the amount of vapor escaping. Okay, now if we make it saturated solution, if this solution is saturated, if we if this solution is saturated and if we heat it, that is if the temperature is increased slowly, then what will happen? The volume of water will start to reduce slowly, but the amount of sodium chloride won't be reduced, and the vapor will escape out. The vapor will escape out through these holes, through these holes. Okay, through these holes, and as a result of that, the volume of solvent will decrease, and supersaturation will not be maintained at all in that case. And to maintain the supersaturation, crystal will start to form. Now crystal forming means reducing the amount of sodium chloride. Sodium chloride will get reduced in volume or amount, and as a result of that, so supersaturation will be maintained. I think you are confused. Let me explain it properly one more time. So we consider a beaker in which there is supersaturated solution of sodium chloride, and it is covered with a lid with small holes in it, and we can control that holes. Those holes allow only the vapor to pass through it. Now if the temperature starts to decrease, then the holes will allow the vapor to pass, and as a result of that, an isothermal condition will be maintained. That means evaporation is happening, but the temperature won't change because there is no vapor that is not passing, or there is no trapped vapor over here. Now due to that, the sodium chloride atoms will start to aggregate and form crystal, and as a result of that, supersaturation will be maintained. Okay, I hope you understood it properly this time. Now, what is the procedure of isothermal evaporation? Look at here. So, the first one is solution preparation. So, in it, a saturated solution of the desired material is prepared at a specific temperature. This solution contains the maximum amount of solute that can be dissolved in the solvent at that temperature. Okay, so a supersaturation solution is prepared. Now, seed crystal introduction. Here in this process, a seed crystal is introduced. Okay, seed crystal will behave as scaffold. So a small high quality seed crystal of the desired material is introduced into the saturated solution. This seed crystal acts as a nucleation site for the further crystal growth. So as the temperature decreases slowly, a seed crystal of the desired same material, okay, will be introduced into the solution. Now this will behave as scaffold. That means more and more atoms will approach it and make aggregate near it, and it will increase the size of the crystal. Okay, now the third step is evaporation. The solution is placed in a controlled environment, typically a sealed container, and allowed to evaporate slowly. So we need to allow it to evaporate slowly. As the solvent evaporates, the solution becomes supersaturated, and the excess solute begins to deposit onto the seed crystal. I've already explained it, right? Now, the fourth step is crystal growth. The solute molecules from the supersaturated solution attach themselves to the seed crystal in an orderly manner. So, crystal will start to grow following the crystal lattice structure. Okay, this process continues as long as the solution remains supersaturated. So, as long as the solution remains supersaturated, the crystal growth will keep on happening. Now, the fifth step is crystal harvesting. So once the desired crystal size is achieved, the crystal is carefully removed from the solution. That is, the harvesting of the crystal is done. Now, there are key factors affecting crystal growth. So, the solvent selection is the first one. The solvent should have a moderate solubility for the material and should not react with it. So this is the condition for solvent selection. That is, the solvent should not react with the crystal. Now, temperature control. Maintaining a constant temperature is crucial to ensure slowly and controlled evaporation. Evaporation rate. A slow evaporation rate promotes the formation of high quality crystals. Similarly, seed crystal quality. It should be high, right? The seed crystal should be perfect and free from defects. Now, similarly, the next one is solution purity. Impurities can hinder crystal growth and affect the crystal quality. I'm not going to explain it one by one because you can easily understand it just by reading it. Now, there are certain advantages of isothermal evaporation. They are simplicity. This is also very simple process, and this is cost effective as well, and a high quality crystal can be formed by this method. Now, there are certain limitations of this method or disadvantage. That is slow growth rate. This process is very slow, okay, for larger crystals. Similarly, this method is sensitive to disturbances. So a small amount of disturbance or a small disturbance can disrupt the formation of crystal, okay. And similarly, limited material suitability. Only high quality materials should be used, and not all materials will be suitable for this method. Now, these are the applications of this method. So, the isothermal evaporation method is widely used to grow single crystals of various materials, including inorganic salts, organic compounds, metal organic frameworks, proteins. Okay, and by carefully controlling the experimental conditions, high quality single crystals can be obtained for various scientific and technological applications. So, I hope you understood this method. Now, the third one, that is flux growth method. So, a flux is a solvent that remains molten at high temperatures and facilitates the dissolution and crystallization of the desired material. So, if we take a solid, if we take a solid and if we increase its temperature, and after certain temperature this melts, this melts without without breaking into different constituent, this just melts, then we call it flux. And this can help to dissolve, this can help in the dissolution and crystallization of the desired material. Okay, now idea, this method, that is flux growth method, is ideal for materials with high melting points or when slow cooling is required for high quality single crystal growth. Okay, now, the key steps involved in this process, that is flux growth method, are: the first one is mixing the solute and flux. So, a flux material should be taken and the solute should be mixed to it. That is, combine the solute and flux in a crucible. Okay, typical ratios range from 1 is to 10 to 1 is to 100. That means the flux should be taken in a large amount, the solute should be taken in a small amount, okay, to ensure sufficient dissolution. Similarly, the second step is heating. So heat the mixture to a temperature above the melting point of the flux. That means the flux should melt, but below the decomposition point of the solute. Solute should not decompose at any further temperature. Okay. So the flux should be melted, but it should not be heated to very high temperature where the solute actually get decomposed. Okay, so maintain this temperature for a sufficient period, ensure complete dissolution of the solute. So if we maintain that temperature at which the flux is melted for a sufficient temperature, for a sufficient amount of time, then we can ensure the dissolution of the solute. Solute will dissolute. Now the third step is cooling. So slowly cool the molten solution at a controlled rate. So slowly the molten solution is cooled. You can see over here 0.1 to 10 degrees Celsius per hour. The cooling speed should be very low. Okay, this allows the solute to crystallize out of the solution as the temperature decreases. So as the temperature decreases, the solute will crystallize out. They will form a crystal. Okay, the solute will form crystal. Now the fourth step is harvesting the crystal. So once the solution cools to room temperature, separate the crystal from the solidified flux. A solidified flux which was formed by reducing the temperature uh, the crystal should be separated from that. Okay, this can be done by, so there are two steps, there are two methods by which harvesting of crystals can be done. They are the flux dissolving the flux in a solvent that does not affect the crystal. So this flux with the solute or crystal is dissolved in a solvent where the flux get dissolved but the solute is not dissolved. Now another method is mechanical separation, that is gently breaking the flux. The flux is taken out and we break it gently and extract the formed crystal. Similarly, the fifth one is post-growth processing. So clean the crystals using appropriate solvents or acids to remove any residual flux. So the extracted crystals is the extracted crystal is cleaned with an appropriate solvent or acid to remove the residual flux. Inspect the crystals for quality and size. That is the last step to be done. Now, there are certain advantages of this method. They are suitable for growing high quality crystals for refractory materials, allows for controlled growth rates, reducing the likelihood of defects. So, there won't be a lot of defects. Applicable to a wide range of system, including oxides, silicates, and materials. So, these are some of the advantages of this method, that is flux growth method. So I hope you understood everything that I just taught in this video. That's all in this video. If you like the video, please share this video as much as you can. And thank you for watching the video. And please don't forget to subscribe my channel to make my face look like this. Bye bye.